Today we're going to talk about the constant volume gas thermometer. In the previous video we mentioned about the alcohol and mercury thermometers, and we mentioned a flaw with them. For example, if we take the alcohol thermometer, the alcohol boils at a temperature of 85 degrees Celsius, so we cannot measure a substance that has a higher temperature than 85 degrees Celsius, since you'll have a incorrect reading. So, what about the constant volume thermometer? Here we have a sketch of a constant volume thermometer. Here we have a container with a certain type of liquid in it. Then we have a flask with a certain type of gas, and that flask is connected through tubes to another two flasks where we have mercury inside of them. And the idea is that this gas has a certain pressure in it, and we'll adjust the volume or the height of the mercury inside this flask in order to adjust the level of mercury here in order to be zero on this scale, in order to know the correct temperature of the gas inside the flask or the container. So we'll inspect two cases. First of all, in this container we'll put water at 0 degrees Celsius, and then we will inspect what will happen to the pressure and to the level of mercury in this flask. So if you put ice water in this container, the gas will have a certain pressure, and we will have to adjust the level of the mercury in order to get here a reading of 0. And this is very useful, so we can know the correct pressure of the mercury, and we will have to either add or subtract mercury from this container in order to get the correct reading. So basically the pressure in this container where the gas is filled will be equal to the atmospheric pressure, or PO, plus R, or the density of mercury, times G times H, and H is the height of mercury. And through this formula we will know the exact pressure of the gas in the container at 0 degrees Celsius. And then if we replace the ice water with water at 100 degrees Celsius, we will again get a reading for the height of the mercury. And in this case, compared to the ice water in the previous case, here we have to add mercury, since the pressure will be much higher than in the first case with the ice water. And then we will know the exact pressures at the exact temperatures. And also it is very important to note that it doesn't depend either the pressure or the temperature on the type of gas. We can use different types of gases and we'll get the same result. Of course, if we keep the temperature well above the temperature at which the gases liquefies. So if we draw a diagram here, and we'll say that the x-axis is the temperature in degrees Celsius and the y-axis is the pressure. And through experiments it has been found out that the pressure of a substance and also the temperature of a substance have a linear relationship. And here at this point on the y-intercept, here the temperature is 0 and we have the pressure at which the gas was when we filled the container with ice water. And here at this point we have when the temperature is 100 degrees Celsius and the pressure of the gas at 100 degrees Celsius. But what will happen if you continue this line until it reaches or intersects the x-axis? Well, what we will see is the point where the pressure is equal to 0. This point is called the absolute 0 point, and the temperature at this point is minus 273.15 degrees Celsius. This is called the absolute 0 point, since at this temperature the motion of molecules ceases completely, and if we continue to, if for instance we have a lower temperature, pressure would equal negative values, which doesn't make any sense. So the absolute 0 point is the lowest point that any substance can have. Okay, now it's called the absolute 0 point because minus 270 degrees 0.15 Celsius is equal to 0 Kelvin. And now we'll jump in a little bit into temperature scales, and we'll study about the Kelvin scale and the Fahrenheit scale. So if you have a temperature given in Kelvin, we can transform it into Celsius by subtracting the temperature in Kelvin minus 273.15. Okay, and what about the Fahrenheit scale? Well, if we have the temperature given in Celsius, you can transform it so we have to multiply by 9/5 the temperature in Celsius, then subtract 32 degrees Fahrenheit, and we'll get the temperature in Fahrenheit. But what's really interesting about the Kelvin scale is that it's the absolute scale. Meaning, for instance, in the example with the constant volume thermometer, the pressure of the gas at 0 degrees Celsius and 100 degrees Celsius varies according to the atmospheric pressure. So, in order to solve this issue, what scientists have done is you have the same graph here. On the x-axis we have the temperature, and the y we have the pressure. We need to take two absolute points for which the temperature is the same regarding or not depending on the pressure or the atmospheric pressure. So the first one was the absolute 0 point, and the second point is something that's called the true intersection point, or the point at which the temperature is 0.01 degrees Celsius. At this temperature, or if you put it into Kelvin, that's 273.16 Kelvin. At this temperature, we can find water into liquid, gaseous, and solid states, and we can find water in those three states at equilibrium positions. So we'll get something like this. Okay, so that's all for today. In the next video we're going to study about thermal expansion on solids and liquids, and then we're going to continue with the ideal gas law.